Imagine a universe where everything, every star that blazes in the night sky, every atom in your body, every force that shapes the cosmos, could be explained by a single, elegant rule. This is the promise and the ambition behind geometric unity, a bold idea that aims to unite all of physics under one grand geometric umbrella. To understand why geometric unity is so compelling, let's first look at where we stand today. Modern physics is built on two towering pillars, each with its own set of rules and language. The first is general relativity, the masterpiece of Albert Einstein. This theory revolutionized our understanding of gravity, showing us that what we perceive as a force, pulling objects together, is actually the result of massive bodies bending the very fabric of space and time. Picture a stretched trampoline. Place a heavy ball in the center, and the surface curves around it. Roll a marble nearby, and it spirals inward, not because of an invisible force, but because the ground beneath it is sloped. That's gravity, according to Einstein, a geometric warping of the universe itself. The second pillar is the standard model of particle physics. This is the rule book for the tiniest building blocks of nature, particles like electrons, quarks, and neutrinos, and the fundamental forces that govern their interactions. The standard model explains electromagnetism, which allows electric currents to flow and lights up our cities. It describes the strong and weak nuclear forces, which bind the cores of atoms together and govern radioactive decay. This framework is astonishingly successful at describing the subatomic world, and it's been confirmed by decades of experiments. But here's the problem. These two frameworks don't fit together. When physicists try to use both sets of rules at once, say to describe the core of a black hole or the moment of the Big Bang, the math falls apart. It's as if one recipe is written in English and the other in ancient Greek, and somehow you're supposed to cook a meal using both. This disconnect has haunted physics for nearly a century. The dream then is to find a single theory, a theory of everything, that unites these two worlds. This is where geometric unity comes in, an idea proposed by mathematician Eric Weinstein. Weinstein asks a provocative question. What if the universe is governed by one master rulebook? And what if that rulebook is written in the language of geometry? Einstein already showed us that gravity is geometry. Massive objects curve space and time, and that curvature guides the motion of planets, stars, and galaxies. Weinstein's insight is to take this one step further. What if all of physics, not just gravity, but every force and every particle, emerges from the geometry of a vast hidden structure? To grasp this, we need to stretch our imagination. We're used to thinking of the universe as having 4 dimensions, 3 of space, length, width, height, and 1 of time. But geometric unity suggests that reality might be far richer and stranger, comprised of up to 14 dimensions. Where are these extra dimensions? Why can't we see them? Think of a garden hose lying on the ground. From a distance, it looks like a simple line, a one-dimensional object. But zoom in, and an ant crawling on the hose discovers a second dimension. It can walk around the hose's circumference. This extra dimension was always there, but it was hidden from our view, curled up so tightly that we never noticed it. Geometric unity proposes that at every point in space there are 10 extra dimensions, curled up so minutely that they're invisible to us. The different particles and forces we observe, the stuff of the standard model, might be the result of how geometric structures twist, turn, and vibrate within these hidden dimensions. Imagine a guitar string. Pluck it one way, and you get a low note. Pluck it another, and you get a high note. In the same way, the different notes played in these extra dimensions could correspond to different particles and forces in our universe. But as captivating as this idea is, the mathematics it requires is staggeringly complex. Describing the geometry of a 14-dimensional space is a challenge that pushes even the brightest minds to their limits. Weinstein has worked for years on the mathematical framework of geometric unity, but the details are so dense and abstract that only a handful of experts can follow the arguments. This makes it difficult for the wider scientific community to check the theory, to see whether it's correct, or even to fully understand what it's claiming. In science, though, a beautiful idea needs to do more than just look elegant on paper. To become accepted, a theory must make predictions, statements about how the universe should behave that can be tested by experiment or observation. So far, geometric unity has not produced new predictions that distinguish it from existing theories. It remains an intriguing possibility, a work in progress that has not yet met the rigorous standards required for scientific acceptance. That doesn't mean it isn't valuable. Throughout history, bold and creative ideas, even those that turn out to be wrong, have often led to breakthroughs. They push us to think differently, to challenge our assumptions, and sometimes to uncover new truths that were previously hidden. The quest for a unified theory remains one of the grandest challenges in science. Whether geometric unity ultimately succeeds or not, it represents the spirit of exploration that drives physics forward. Perhaps the universe really is governed by a deep, underlying geometry, a cosmic harmony that explains everything from the orbit of planets to the flicker of particles. Or perhaps the true answer lies elsewhere, waiting to be discovered by the next generation of thinkers. For now, geometric unity stands as a testament to human curiosity and imagination. It reminds us that the universe may be far more mysterious and far more beautiful than we ever dreamed. The search continues, and with each new idea, we come a little closer to understanding the deepest secrets of reality.